Welcome to the lecture on functions. We're going to start by talking about what's called a relation, which is a general set of any ordered pairs, and it's basically a correspondence that maps x values to y values. So we send x's into y's. There's very different notations that you can use to represent a relation, and the first one that we're going to talk about is what's called a list, and that just lists your x comma y's as ordered pairs and just uses these curly braces to designate your list of all the ordered pairs in your relation. The next kind of representation that you might often see for a relation is what's called a correspondence or a mapping. And if we use the same set of ordered pairs that are in our list and write that as a correspondence, then it's going to look like this. We would take our -1 and we would draw an arrow to 3, the y value that it gets mapped to. Then we would have 2 get sent to 4, 6 gets sent to 1, and 6 also is getting sent to 2, so I can draw kind of a double arrow coming out from 6. Sometimes you also will see circles around these values so that you can kind of see the set of all your x's and the set of all your y's. So this is called a correspondence or a mapping. The last way that you often see a relation listed is as a graph, and this would just map your ordered pairs into points on a coordinate axis. So -1 comma 3, we would just go -1 for x, up 3 for y, and put our dot. 2 comma 4, over 2 up 4, and then 6 comma 1, and 6 comma 2. So you just get a set of dots. So this is what our relation would be, either a list, a mapping, or a graph. Some vocabulary that you need to be familiar with when we talk about relations and functions is the first word here, domain. A domain is the set of all your inputs, and since our inputs here are being associated with x values, you want to think of your domain as all of your x's. So in this example up here, if you think about your list or your correspondence or your graph, you would want to write your domain as all the x values that were used. And that's really easy to see from our mapping over here. We used the x values -1, 2, and 6. So to write this as a domain, we could just write curly braces, -1, comma 2, comma 6, close it with curly braces. So this whole set would be considered your domain. Now when you see the word argument, the argument is referring to a specific input value or a specific x value. So I could say the argument -1, or the argument 2, or the argument 6. So an argument is one specific x value. When we talk about the range is just like the domain, except now we're going to refer to all the outputs. So the range is going to be all of our y's. So if we look at our mapping again, everything that's in this second circle is going to be our range. So writing this as a set, you can put these in numerical order just to make it look a little bit cleaner. So this would be the set 1, comma 2, comma 3, comma 4. And that whole set is called our range. And then the image is one specific output value or one specific y value. So just 3 or just 4 or just 1 or just 2. So to practice some of this new vocabulary, what would it mean if I said find the image of the argument 2? So if we were to rephrase this, remember image is a y and argument is an x. So this is really saying find the y when the argument x is 2. So if we look at our correspondence mapping, or even if we go up to our list with ordered pairs, which one of these ordered pairs has an x value equal to 2? That would be this ordered pair right here, 2 comma 4. So when x is 2, what is y? Y is 4. So our answer here would be the image is 4 when the argument is 2. Okay, if we try another example, find the argument of the image 2. So this time we want the image to be 2, and we're looking for the argument. So if we think of this in terms of x's and y's instead, this is saying find the argument x when the image y is 2. So now if we go back to our ordered pairs, which ordered pair has a y value equal to 2? So if you look at all your y values, this is the one where y is 2. What's the x when y is 2? The x is 6. So the argument would be 6. Okay, last example. 1 is the image of what? So 1 is the image of what? So we want the image, which is y, to equal 1. So what does that correspond to? So if we look at our ordered pairs, if the image y is 1, which of these ordered pairs has a y value of 1? That would be this one right here. And what's that the image of? What's the x of that? It's coming from 6. So 1 is the image of 6. Okay? So a relation is a very general idea. It's basically any kind of correspondence or mapping between x's and y's. What we're going to do is sort of tweak that definition slightly and define something called a function. A function is a specific type of relation that sends every input to exactly one output. So every x value, every input x, gets sent to exactly one y. So let me give you 2 examples here. The first one is going to be an example of something that is not a function, and then I'll give you something, an example of something that is a function. So if you think about spam email, you've probably received lots of these in your experience. A spam email takes a single message and sends it out to multiple recipients. So a single input, the email, is getting sent to many, many different outputs. That's exactly what we don't want to happen, because in a function, every input needs to get sent to exactly one output only. So for every x, there should be only one y coming out of it. So you don't want to see these multiple arrows coming out of your inputs. So this is not a function. Okay? So something that would be a function would be regular mail that you receive from the mailman. And the reason why this is a function is if you have several letters being delivered, you can't take a letter, rip it in half, and send it to 2 different mailboxes. That's not allowed. So if you have a letter coming in the mail, it can only get put into a single mailbox. Now you could have all these different letters getting sent to different mailboxes. That would be fine. Or you could have various letters all getting sent to the same mailbox. You get lots of pieces of mail at one time. So this is also a function over here, and sometimes this is confusing for students. We do have multiple arrows, but they're multiple inputs getting sent to one output. That is okay for a function. Notice that from each input, each of these letters, there's only one arrow coming out, as opposed to our spam email example, where we have a single input with many arrows coming out. That's what we don't want to see. It's okay if all of your inputs get sent to the same y. We just don't want a single input getting sent to many y's. So both of these examples over here are functions. Okay? So in the next set of examples, we're going to be given different relations, and we're trying to decide, first of all, is it a function or not? Yes or no, and then also decide what the domain and the range of the relation is. So if we look at this first graph here, we want to decide, is it a function or not? And what you want to notice here is when you look at these different points, remember the x values are the inputs and the y values are the outputs. And this is not a function because we have what I would call two vertical points right here. If you think about what the coordinates of those points are, they both have x values of -3. This upper point has a y value of -1, so -3 is kind of getting mapped to -1. And for the lower point, the y value is -4. So we also have -3 getting mapped to -4. So right there is your double arrow coming out of the x value -3. We don't want to see double arrows. We don't want to use the same input twice. So that's why this is not a function. To list the domain, what we're going to want to do is list all of the x coordinates that got used here. And since there are only 4 different x values that got used, we're going to list this as a set. So I'm going to use curly braces. And just thinking left to right here, the first x value for both of these points was -3. I'm only going to list it once, even though it got used twice. The next x value for this point right here is -1. The next point over here has an x value of +1. And the next point over here, 1, 2, 3, 4, 5, has an x value of 5. So we had 4 distinct x values, so I'm listing those as a set. For the range, we're going to also make a set of values. This time the range is the y's. So I like to think of the lowest point up to the highest point, and that way I can write them in numerical order. So the lowest point would be down here. That y value was -4. Then these 2 points here both have the same y value, -1. We only need to list the -1 once. The next point here has a y value of 0. And the highest point up here had a y value of 2. So we have our domain and our range, and this was not a function because we had 2 vertical points, 2 points that shared the same x value but had different y values. In the next example, we're given our relation as a list. So we want to decide if this is a function. Sometimes it's easy to determine if something's a function or not by rewriting it as sort of a mapping. So this would be the same as taking -1, mapping it to 2, taking 5, mapping that to 4, and 6 also gets mapped to 4. So this is a function because I have no double arrows coming out of any of these inputs. Notice that the y value 4 did get used twice, but we didn't use any x value twice, so that's why this is a function. For your domain, we have 3 ordered pairs here, and my domain is going to be the set of all the x's that got used. So -1, 5, and 6. And for my range is all the y values. And notice over here in my mapping, the only y's that got used were 2 and 4. So I'm just going to write the set 2, 4. And you only need to list the 4 once, even though it got used twice. For our last example here, is this a function, yes or no? And your answer should be no, because we have our 1 with a double arrow coming out of it. So 1 got used twice, it got mapped to 5 and to 6, and that's not allowed for a function. The domain is going to be the set of all these inputs, so using set notation, 1, 2, 3. And for the range is going to be all these y's, so the set 5, 6, 7, 8. Okay? Now, those examples all had distinct points. So when we wrote our domains and our ranges were written as sets. In the next few examples, we're going to have nice connected graphs. So when we write our domains and ranges for these, we're going to be using not sets, but intervals, interval notation. And we're also going to be using a new test called the vertical line test, which is an easy visual test to use to determine if something is a function or not. And what the vertical line test says is that a graph that you're looking at will be a function if there's no vertical line that intersects your graph in more than one point. So if we look at this first example, what you want to visualize are vertical lines intersecting your graph. If you can find a vertical line that intersects your graph more than once, which these do because they intersect on the top and on the bottom, then you will have no function if your vertical lines are intersecting more than once. If your lines intersect no more than once, then you do have a function. So these points intersecting twice mean this is not a function. And think about our previous example. The reason why is because you have these vertical points where the same x value is being shared, but they are using different y values. So this would be, the point -2 comma something positive, and the -2 value something negative. So -2 is getting used twice, and that's not allowed for a function. If we use our vertical line test on the next example, no matter what vertical line I draw, each vertical line is only intersecting once, and that's a good thing. That means we do have a function. On the last example, if I draw my vertical lines again are intersecting twice, so I have vertical points, x's are getting used twice, so this would not be a function. Now when we go to write our domain and our range, remember what I was saying earlier. These are nice connected graphs. So when you are trying to write the domain and the range where all your points are connected with a smooth curve, you want to be using interval notation. So connected graphs have domains and ranges with interval notation. So remember, interval notation uses parentheses or brackets. When we did our previous examples up here, these were not connected graphs. If you look over here, we just had a bunch of dots. So when you have disconnected graphs, then your domains and ranges should be sets. So your domains and ranges will be sets. And you're going to want to use set notation. So that's with the curly braces, and you just make a list of points. Okay? So we already did that up here using set notation. Let's go down here and try our interval notation. When you think about your domain, remember that domain is x's. So we want to think about what x's is this graph going through. And when you think x's, you want to kind of think along that x-axis. Think left to right. What point on the left does my graph sort of start at, and what point on the right does my graph sort of stop at? So what x's do I go through? And in this example, our leftmost point starts at -4, and it goes all the way up to +4. So I want to include all the x's in between, since my graph goes through everything, including all the decimals and all the fractions in between. So that's why we're going to use intervals. So this is going to start at -4 and go up to +4. Notice that I'm using brackets because I actually hit -4 and +4 and go through those points. For the range, we want the y values. So for y's, you want to think along that y-axis up and down. So to get this in the right order, think of your lowest y value up to your highest y value. So think of your lowest point up to your tallest point. What y values do those go through? The lowest point here has a y value of -2, and I go up to a y value of +2, and I hit all the y's in between, including all the decimals and fractions. So my range should be -2 up to +2. Using brackets again because I hit those points. And remember, when you use interval notation, it's always the smaller number on the left and the larger number on the right. So in the next example for our domains, which are our x's, think left to right. What x on the left do I sort of start at, and what x on the right do I sort of stop at? In this example, I have arrows. So this graph actually will continue to go up and to the left and up and to the right. So there is no starting x value over here on the left and no stopping x value on the right, because my graph will just continue to go towards minus infinity on the left and positive infinity on the right. So in this example, we would say that our domain is minus infinity up to plus infinity. And the convention is that whenever you use negative infinity or positive infinity, you always use open parentheses around them. Because these aren't really numbers, we don't contain infinity, we don't hit infinity, we just approach it. Okay, for the range, think about up and down. What's the lowest point that we go up to, and what's the highest point we go up to? So the lowest point we sort of start at here is right here at the origin, and that y value is 0, and then I just go up from there towards infinity. So this range would be 0 up to infinity. I'm including the 0 because I actually hit it, and I go up to infinity and there's a parentheses around the infinity. Okay, for our last example, our domain, our x's, thinking left to right. Where do I start on the left? This x value over here is as far over as I go, and it has an x coordinate of -4. And I actually hit it, so I want to have a bracket around it. And then I just continue going to the right because of these arrows. So this is going to continue going towards infinity. Parentheses around the infinity. For the range, notice because of the arrows, I'm going to continue going downwards and continue going upwards. So there's no lowest point or highest point because the arrows make me continue going down and going up. So the range here for y's would be minus infinity up to plus infinity. Okay, so one thing you definitely need to be able to do with functions is determine if you have a function or not, yes or no, and also determine the domain and the range. So you would definitely be asked to do that. The next major thing that you'll be asked to do with functions is evaluate them and use the correct function notation. So let's talk about that next. When you talk about function notation, this is what you use if you have an actual formula or a rule for your function. In all the other examples we've done so far, we haven't really seen a rule or formula. We've just seen a set of points or a graph. So this function notation is only going to be used when you have a formula. And the notation looks like this. This would be f of x equals x squared. F is the name of your function. Typically functions are named with F, G's, or H's, but really any letter of the alphabet or any symbol will work, but typically F and G and H are used for functions. The input variable is always what you're going to see inside of these parentheses. And again, most commonly we use an input variable of x, but it doesn't have to just be x. You could see t, you could see a, you could see s, whatever. It doesn't really matter. On this side of the equals is where your output rule is going to be found. And it's going to be in terms of whatever the input variable was. The way we would say this in words is we would say f of x is x squared. So f of x is the way you sort of pronounce this notation. This rule over here would then be g of x is 2 times x minus 3, for example. Now, a lot of times when I'm first learning about functions and first teaching about functions, I like to think of our functions very generally. Instead of just thinking of it as f of x equals x squared, you can think more generally and think of this as f of stuff equals stuff squared. So that's what this notation is. when we're first learning how to use function notation, it's sometimes helpful to rewrite your function not in terms of x, but in terms of any input at all. So this could be f of whatever equals whatever squared, or g of stuff equals 2 times that stuff minus 3. So it's just an alternative way to think of your function. So then if you go to evaluate a function and you want to know what f of 4 is, this means take 4 as your input and you're going to substitute it in for your rule. If you're thinking in terms of x's, then this is letting x be 4, and we would substitute in 4 for this x. If you're thinking more general, f of stuff equals stuff squared, then this is saying take f of 4, and so we need to take 4 and square it. So this is going to be evaluated by just substituting 4, squaring it, and we know that 4 squared turns into 16. So f of 4 equals 16. Remember that the x was the 4, so that means this 16 is like the y, and that means this is sort of like an ordered pair, 4, 16. Okay, let's try g of 6. So now we want x to be 6, the input is 6, and we want to substitute in x into our rule for g. Or if we go over to our more general notation, we're going to put 6 inside these boxes. So we're substituting in 6, and we would want 2 times 6 minus 3, and then we just want to simplify that. 2 times 6 is 12. 12 minus 3 is 9, so our answer would be 9. Now when we go to f of a, notice this time I'm not substituting in a specific number, I'm substituting in a variable. And this is where students sometimes get a little bit confused. What we're going to want to do instead is use this notation over here with this box, and this time we're going to substitute in a for our input. So I'm just going to put an a in my input position here and also here. Or in other words, we're substituting in a in terms of x instead of x. So instead of f of x, we want f of a, and that just becomes the a squared. And we can't simplify that because we don't know what a is. So our answer is just going to be a squared. So if your input is a variable, then your output is also going to involve that variable. Okay, if we go to the next one down here, f of a plus b, this time we want to substitute in a whole expression in for our stuff. So when I go to my boxes over here, we're going to substitute in not just a, we're going to substitute in a plus b. This whole expression here becomes my input. So a plus b is going to be the new input. So we're going to put a plus b inside of our box. And so the rule for f says take whatever your input is and square it. So we're going to take our input a plus b and square it. And to make sure that I do this properly, make sure you wrap your entire input in parentheses. So we're going to have a plus b quantity squared. Now this is an acceptable answer, but I also want to review with you how you could expand that out. And if you remember how to do this from our discussion on foiling, this is like a plus b times a plus b. So the long way would be to FOIL this out, first, outer, inner, last. Or you should remember that there's a pattern for this. This is a square of a binomial pattern. So when you expand this out, what you're going to get is the a squared, the b squared, and that's always positive, and there's going to be a middle term, which is these two multiplied together, doubled. So a times b is ab, doubling it gives me 2ab, and since this was a plus sign in between, my middle terms will also be plus. So both of these answers would be correct. This is just in the factored form, and this is in the expanded form. Okay, so let's try another example with g, and this time we want g of the quantity a plus b. So a plus b is going to be our stuff, it's going to be our input. So in my rule for G, I'm going to be substituting in A plus B in for this box. And when I do that, remember you want to wrap all of that stuff in parentheses so that when we do 2 times that input, we're remembering to distribute that 2 across later on. So the rule for G is take 2 times the input minus 3. So 2 times the quantity A plus B minus 3. And you could leave it like that, but most likely I would go ahead and distribute that 2 across and make this 2A plus 2B minus 3. And there would be my answer. Okay? Now in the next example, we have f of A plus B minus f of A. So this is a pretty common example that you'll probably be asked to do. You want to get used to it and get familiar with how to do this. So this example actually uses the function twice. We're going to use the function f and input in A plus B, and then we're going to use the function again and input in A. So we have two different times we're going to be using this function f. So let's do both of them. I'm going to do f of A plus B, and then I'm going to do f of A over here, and we're going to want to subtract both of those answers. So remember how to get f of A plus B. You take A plus B, and you're inputting it into your rule for f, which says take whatever your input is and square it. So we're going to take A plus B, and we're going to square all of that. So this is going to look like A plus B, wrapped in parentheses, all squared. Okay, so that's our f of A plus B. Now if we want to know what f of A is, then instead of substituting in A plus B, we're going to substitute in just A. So we're just going to put A in our little box. So f of A would just be the A squared. So if I write that down over here, f of A is just A squared. So we have A plus B quantity squared is our f of A plus B. A squared is our f of A. And remember what we're supposed to do with these two things. We're supposed to subtract them. So this is initially what your formula is going to look like. Now you do want to expand out A plus B squared in this example because there is going to be some cancellation happening. So remember when we squared this out, we squared the A squared, we square the B squared, and the middle term is these two multiplied together, doubled, so that's going to be a positive 2AB. Now over here with this minus A squared, we'll see that the 2A squared terms cancel out, and this simplifies to 2AB plus B squared. And here is our final answer. Okay? Now we're going to do this all over again, but with some slightly more complicated functions. So we're just going to evaluate a few more functions here. So in this next example, we're going to find f of x plus h minus f of x. So again, it looks very similar to the last example. Instead of a plus b, I have x plus h, and instead of f of a, I have f of x. So we're going to want to find f of x plus h, and then we're going to want to find f of x, and we're going to subtract these two answers. Now this time my function f is going to be given to me up here at the top, and it's a little more complicated than our last function. Instead of f of x equals x squared, it's f of x equals x squared minus 2x plus 1. So to make sure that I evaluate my function correctly, let's write out this more general form. Instead of just f of x, let's think of f of stuff. And the rule here says to take your input and you square it first. So we're going to square our stuff, and then we're supposed to subtract 2 times that same input plus 1. So there's my new, more generalized rule for f. And what we're going to do is substitute in x plus h. So I'm going to put x plus h here, here, and here. And this is the place where students sometimes get confused. When we substitute in x plus h, we need to make sure that we substitute it in for this x and also for this x. So this whole quantity goes here and it goes here. So let's write out what this turns into. We get our x plus h, and we're supposed to square that first. So that's this part right here, minus 2 times our new input. So instead of 2 times x, it's 2 times x plus h. And then on the end, it's just a plus 1. So it's this same rule that we have right here, just using parentheses around that x plus h quantity. So all of this became my f of x plus h. Now what we want to do with that is subtract just f of x, not f of x plus h, but just f of x. So now I'm going to substitute in just x in for my stuff. And if we do that, we're going to have inside these boxes just an x. X here, and x here. So that's the exact same rule we were given. F of x is x squared minus 2x plus 1. So all of that stuff is our f of x. So here's our f of x plus h. Here's our f of x. And now what we want to do is subtract these two things from each other. And here's a really common mistake. When we subtract f of x plus h minus f of x, remember that all three of these terms right here made up f of x. So we want to make sure that we subtract all three of them from this quantity up here. So you must have parentheses around all three of these terms, because in the next step we're going to be distributing that negative across. Okay, so let's go ahead, and there is going to be lots of cancellation on this example, so we want to make sure that we expand out our square, we distribute our negative 2, and we distribute our negative across our f of x. So we have lots of stuff to do next. The first thing I'm going to do is distribute this square. So I'm going to simplify and expand out this quantity right here. So that's going to turn into the x squared, the h squared, and remember this is FOIL going on right here. So we do get a middle term, the x times the h doubled. So you get x squared plus 2xh plus h squared. A lot of times students forget to FOIL there and they forget that middle term, so please be careful. In the next term here, we're going to distribute this negative 2 across, so that's going to give me a minus 2x and a minus 2h, and then this plus 1 is just going to carry down. So all of these terms here came from f of x plus h. Now what we need to do is distribute our negative across to our f of x, and that's just going to change these signs, so we get minus x squared plus 2x minus 1. So here's all of my terms expanded out. Now all we want to do is see what's going to cancel. The x squareds cancel, the 2x's cancel, the 1's cancel, and all we're left with are terms with h's. So we have a 2xh plus h squared and then minus 2h. And this is a very common thing that will happen. If you're doing this correctly, all of your terms that don't have h's should cancel out, and your final answer should have h terms only. So here's my final reduced answer. I can't do anything further with this because none of these are like terms. So here's our final answer. Okay, so that's a hard one right there. F of x plus h minus f of x. But a lot of instructors expect students to be able to do this, so you're going to want to practice this kind of example so that you get really good at it. Okay, the next function evaluation that we want to do is 2 times f of x plus 1. Notice here that the 2 is on the outside of your function. So when we do this, we're going to want to do 2 times whatever f of x plus 1 turns out to be. So let's figure that out. Let me erase a few things here. So to figure out what our function is, evaluated correctly, we're going to want to take our function f of x and remember that it's our input squared minus 2 times our input plus 1. So this time around, our input, our stuff, is this x plus 1 quantity. So we want to take x plus 1 and put it right here. We want to put it right here where that square is, and we want to put it right here after that too. And to do it correctly, wrap this x plus 1 in parentheses. So f of x plus 1 should turn into x plus 1 squared minus 2 times x plus 1 plus 1. So where we had x's before in the original problem, we replaced those x's with x plus 1's. So we want 2 times all of that stuff. Now, because of order of operations, when we go to simplify this, you want to make sure that you simplify everything in these parentheses first before you multiply by that 2. So when I go to distribute here, we're going to do that last. Leave the 2 out front for now, and to clean this up, we're going to want to do this squaring first. So using our FOIL, x squared becomes x squared, 1 squared is 1, and the middle term will be x times 1 doubled, so that's just going to be a 2x, and it's positive because my sign was positive. So that's the square. Now I'm going to distribute my negative 2 across, so we'll get minus 2x minus 2, and then the plus 1 on the end just stays put. So now we've expanded and distributed and gotten rid of all the parentheses on the inside. Now we just want to combine any like terms here, then we'll be ready to multiply by that 2 out front. So inside these parentheses, notice that the 2x's cancel out, and 1 minus 2 plus 1 goes to 0. Those all cancel out as well. So all we have left in the parentheses is x squared, and so the 2 out front just gets multiplied by it, and here's our final answer. It all reduced down to 2x squared. Okay, the last few examples are going to use the other 2 functions that were listed up above, and the first one here is p of 4. When we want p of 4, notice this time the input here is a specific number, and remember whatever is inside those parentheses, that's what your x is. So we want to let x be 4, and when this is saying find p of 4, that means find y. Find y when x is 4. So let's go up to our function p. P did not have a formula. P was just listed as a bunch of ordered pairs. So out of these ordered pairs, remember we want x to be 4. So which of these ordered pairs has an x value that's 4? This one right here, 4, 1. So the x is 4. What we want for p of 4 is the y. So p of 4 is referring to the output. And the output in this ordered pair is 1. So this answer is p of 4 must be 1. So the input number is what's in the parentheses. And when you see a number in those parentheses, you're looking for the y value that goes with that number. So we're finding the y when x was 4. Okay, in the next example, now we're going to use the function g, and this time we want our x to be 0. Our input is 0. So if we go up to our rule for g, we're going to substitute in a 0 right where these x's are. So if we use our box notation, this says g of stuff is supposed to be the square root of that stuff minus 1. And this time we want 0 to be our input. So I'm going to put a 0 right in that little space. So this becomes square root of 0 minus 1. Now when you go to reduce that, you get square root of -1, and that, you should know, is not a real number. We don't want to have negatives under the square root. So this is not allowed. So for an answer, just put the empty set, or you could write that it's undefined. Either answer would be correct. Okay? For our very last example, we're going to go back to that function g, but this time we're going to substitute in the whole quantity x plus 2. So this is going to be our box right here. So if we go up to our function g, I'm going to take out these zeros, and instead of zeros in our box, we're substituting in that quantity x plus 2. And if you want to wrap that in parentheses to be safe, this is going to turn into the square root of x plus 2 in parentheses minus 1. So we're going to write that down below, the square root of x plus 2 minus 1. And then to simplify here, we actually don't need the parentheses in this particular function because there's no square or no number out front that would need to be distributed. So we can drop the parentheses, and then just combining like terms, plus 2 minus 1 just becomes x plus 1. And so our final answer is the square root of x plus 1. Alright, so for functions, please make sure that you're able to determine if you have a function or not, yes or no, determine the domain, the range, and then be able to evaluate a function for numerical inputs like numbers, and also for expression inputs, things like x plus 2 or a plus b or x plus h. Okay, now we're going to try a couple more examples here that are a little bit trickier because of the notation. So let's take a look at the two functions, 3x squared minus x plus 1, and g of x, which is 5x minus 3. So the first one here says to find 2f of x plus 1 plus g of x minus 4. So notice a couple of things here. First of all, it mentions f and it mentions g, so we're actually going to end up using both functions. The f is using x plus 1 as its input, so that means we're going to take x plus 1 and substitute that in for this x and for this x. We're not going to plug it in over here because this doesn't have an x in it, it's just a constant. So f of x plus 1 would look like 3, and then instead of this x, we're going to put x plus 1 in its place, wrapped in parentheses, but that x is supposed to be squared, so we want to square that whole quantity. Then we're going to subtract x again, but remember our input has changed to x plus 1, keeping it wrapped in parentheses, and then we have our plus 1 on the end. So it should look like 3x squared minus x plus 1, like the original function, but where I had x before, now I have x plus 1s instead. So that represents this part of the problem right here. What about that 2 that's in front? Well, if you think about what that says, that's 2 times this whole function. So the way we want to show that properly is 2 and then times or parentheses this entire function. So that 2 needs to go on the outside. So now we've done all of this part of the problem. Now what we're going to do is add to it whatever g of x is. And g of x has as its rule 5x minus 3. So right there's our g of x. And finally we have this minus 4 on the end. There's no function in front of it, so it's just a constant. It's just a plain old minus 4. So this is what it turns into after we substitute everything in. There shouldn't be any f's or g's left over because we've used the appropriate function. And now all that we have to do is kind of clean this up. So thinking in terms of order of operations, we want to start inside the parentheses first, and then within those parentheses we want to do the exponent first. So we need to square out x plus 1. Remember, when you square x plus 1, that means FOIL. So we're going to get, let me recopy my 2 and my 3. When I square out x plus 1, we get x squared, we get a middle term of 2x, and we get that plus 1 on the end. Then I have my minus x plus 1 and my other plus 1. So all we've done so far is our exponent. Now let's go ahead and distribute our 3 across. So we get 3x squared plus 6x plus 3. Let's distribute this negative across, negative x minus 1. And now we should be able to combine all of our like terms inside of those parentheses. So we still have our 2. We're going to get a single 3x squared term. 6x minus x is 5x. And 3 minus 1 is 2. 2 plus 1 is 3. Alright, we're getting there. Now that we have everything in the parentheses as simplified as possible, we're ready to distribute this 2 across. So we get 6x squared plus 10x plus 6 plus 5x minus 3 minus 4. And finally, we're ready to combine all of our like terms. So we have our 6x squared, 10x plus 5x is 15x, and 6 minus 3 is 3. 3 minus 4 is negative 1. So there's our final simplified answer. Alright, let's take a look at g of a plus g of b. So this is going to use g twice. In the first case, we're going to substitute in a for the input. And notice in our rule for g, wherever x was, now we're going to put a. So we're going to put an a right there. So g of a should become 5a minus 3. Now we're going to do that again, but this time we're going to substitute b in for that x. So if I substituted in b, that would be 5b minus 3. And what do I want to do with these two answers? I want to add them together. So here's g of a plus g of b. Now to clean it up, 5a and 5b are not like terms, so they're just going to stay the same, 5a plus 5b. But a minus 3 and a minus 3 combine to a minus 6. So here's our final answer. Alright, our next example is g of x minus 3 plus 2. So let's remember what g of x is. G of x has as its rule 5x minus 3. So if I want to do g of x minus 3, where x minus 3 is the new input, that is going to go right where this x is. So my new rule would be 5, and then instead of 5x, it's going to be 5x minus 3, and then we have this minus 3 on the side. So again, it kind of looks like the original 5x minus 3 that was the real rule for g, but instead of having x, we've replaced this x minus 3 in its spot. Now what about that plus 2 on the end? Well, the plus 2 on the end doesn't have a function in front of it, so it's just a constant that's going to be added off to the side of whatever we got for g. So here's what it should look like when I first substitute in. Now all we have to do is simplify, so let's distribute our 5. 5x minus 15 minus 3 plus 2. The 5x stays put, and combining like terms, minus 15 and minus 3 is minus 18, and minus 18 plus 2 is minus 16. So here's our final answer. Alright, on the next one we're going to use g as well. This time we have a 2 minus in front. There's nothing in front of that 2, so this is just a constant. It's going to be 2 minus whatever we get for g of xy. Now to do the g of xy, remember that xy is our new input. So I'm going to take whatever I see right here and I'm going to substitute it in where I used to have just plain old x. So the rule for g is 5 times whatever the input is, and this time our input is xy, minus 3. So it's 5 times the input minus 3. Now notice, and this is really important on this problem, you need to have that whole expression, 5xy minus 3, wrapped in parentheses, because we want to subtract all of that away from the 2. And if you don't have those parentheses, then you're not going to remember in the next step to distribute, and it's going to make your final constants be wrong. So minus times minus becomes plus 3. 2 plus 3 is 5. So our final answer will be 5 minus 5xy. Alright, the next one here is f of x quantity squared minus 2 parentheses x plus 3. So let me recopy what f is. It's 3x squared minus x plus 1. So if I want f of x quantity squared, first of all, I want to know what just f of x is, and that's a normal input. That's a normal x in there. So I don't have to input in anything crazy or different or new. I'm just going to use the plain old rule for whatever f of x is, and that's this 3x squared minus x plus 1. So there's f of x. And what do we want to do with f of x? We want to square that whole quantity. So that's what that should look like. Then off to the side, we have this minus 2x plus 3. Notice there's no f or g in there, so that's just an expression that is going to be put off to the side of what we already have. So you don't have to plug anything into f or g for this second part. So here's what we're given. Now all we have to do is simplify it. And that's going to require a little bit of foiling going on here. You might need to do a little bit of scratch work. So let me do some down here. We want to FOIL this out, so I'm going to write it side by side. And that just means we're going to be distributing. We actually have 3 terms times 3 terms, so that means we're going to end up with 9 terms. So we're going to get the first 3 terms from this 3x squared times all 3 of these. So that'll be 9x to the 4th, because you add exponents when you multiply. X squared times x squared is x to the 4th. 3x squared times a minus x would be minus 3x cubed. And 3x squared times 1 stays 3x squared. There's my first 3 terms. Now I'm going to take the negative x times all 3 of these. So negative x times 3x squared is negative 3x cubed. Negative x times negative x is positive x squared. And negative x times 1 is negative x. So there's my next 3 terms. And then my last 3 terms are this 1 times all 3 of these. So a 3x squared, a minus x, and a plus 1. Now if we combine our like terms here, we're going to have just that 9x to the 4th. And then we have a negative 3x cubed and another negative 3x cubed, so that's negative 6x cubed. Then we have a 3x squared plus an x squared plus a 3x squared. So 3 plus 1 plus 3 is 7x squared. And then we have a minus x and a minus x, which is a minus 2x. And then we have that plus 1 on the end. So when I FOIL all this out, I get 9x to the 4th minus 6x cubed plus 7x squared minus 2x plus 1. And then I just need to distribute this negative 2 across, so I get negative 2x minus 6. And that's going to give me just a couple more like terms, so my final answer will be 9x to the 4th minus 6x cubed plus 7x squared. A minus 2x and a minus 2x is a minus 4x, and a plus 1 minus 6 is a minus 5. And here's my final answer. Okay, the last 2 examples here use f again, but in very similar but slightly different ways. So the first one here is saying find f of x over 2. So on this one, we're going to substitute in something new for the input. So instead of just using plain old x, now we're going to replace these x's with x over 2's. So this rule for f will become 3, and then instead of x squared, it's going to become x over 2 squared. And then we're going to subtract, and instead of subtracting just x, we're going to subtract x over 2, and then we have that plus 1 on the side. Now to simplify this, there's not a whole lot you can do with it, but we can distribute this square across, square the top and square the bottom. So x squared is x squared, and 2 squared is 4. And that's about it. These are not like terms because you've got an x squared term, an x term, and a constant. So this would just be your final input, or final answer. Alright, the last example here is pretty similar to that, but it's important that you notice the difference in where that division symbol is. Up in the first problem we did, we were dividing x by 2. Here we're dividing the entire function by 2. So if we take a look at this numerator, the numerator is whatever f of x is, and f of x is just 3x squared minus x plus 1. So we want to take that entire function and divide all of it by 2. And that can't really be reduced at all, so that would be your final answer. So in this example, we were dividing the entire function by 2. In the one previous to this, we were dividing the input by 2. So we get slightly different looking answers. Close, but different. Okay, that concludes our lecture on functions. Good luck.